Hi guys, this is Mr. Robeson. We're back in AP Stats. We are looking at independence and the multiplication rule here, and then we're going to look at some at least problems. All right, so the multiplication rule for independent events. So following the Space Shuttle Challenger disaster, if you don't know, Google it. The Space Shuttle blew up basically. I think it was in '86. It was determined that the failure of O-ring joints in the shuttle's booster rockets was to blame. Under cold conditions, it was estimated that the probability that an individual O-ring joint would function properly was 0.977, or 97.7% of the time. Assuming O-ring joints succeed or fail independently, what is the probability that all 6 would function properly? So in other words, we want the probability that the first O-ring works, and the second O-ring works, and the third O-ring works, and the fourth, and the fifth, and the sixth. All right, now since these are independent events, instead of doing conditional probabilities, we can just break this up into the probability that one fails times, or that works properly, I guess is what we're doing here, then probability of 2, and then the probability of the third one, and then the probability of the fourth one, and the probability of the fifth one, and the probability of the sixth one. Now, it says that the probability that any one of them fails, so whatever number it is, or that any one of them works, sorry, I keep saying fails, we're working here, is 977. So that means this is all just the same one, or this is all just the probability of O to the sixth, because it's happening 6 times. So that is 0.977 raised to the sixth, which gives us roughly 0.87 or 870. So that's about an 87% chance that all 6 of them will function properly. All right, it's a decent percent, but I mean, I don't know if I'd want to, throw my life on the line for that. All right, but I guess what they ended up saying that is if one of them failed, it wasn't a big deal, but if 2 of them failed in the same joint, so like see how the shuttle has little joints, or the rocket booster rocket has little joints here, there apparently were 2 O-rings in each one of those, and if both of them in the same one failed, then it could be a problem. And that was what was the problem for the Challenger. All right, so another looking at the independence rule. So the probability of rolling a 4 on a standard 6-sided die, and then rolling twice and not getting a 4. All right, so rolling a die are independent events. All right, so that means the probability of 4 and then not 4 and then not 4 will equal the probability of 4 times the probability of not 4 times the probability of not 4. So the probability of 4 is 1 out of 6. Probability of not 4 is 5 out of 6. And again, 5 out of 6. So we can just work this out, throw it in our calculator, whatever, and we are going to get 0.116, or 25 over 216, I think is what that works out to. All right, you could leave it like that too if you wanted to. All right, so now at least problems. So we're going to still looking at the multiplication rule, independent events, but now we're going to do at least one. So we got the same situation happening. The probability that it works is 0.977. They fail independently. What is the probability at least one will fail? All right, so the way we do this is we say, well, we know the probability that all 6 work from last time was the probability of O to the 6th, which was 0.87. So that's all of them working. The complement of all of them working is that at least one fails. So the probability that at least one fails is equal to 1 minus the probability that all 6 work. So our answer is just going to be 1 minus the 0.87 or the 0.13. All right, so the probability that at least one fails is just these 13% here. All right, and that makes sense from last time. So the probability that all of them worked was 87%, So the other thing that can happen is 13%. And the other thing that can happen is that 1 could fail, or 2 could fail, or 3 could fail, or 4 could fail, or 5 could fail, or 6 could fail. And this is me with the space shuttle. I don't remember which one that was, but that was the one at the Smithsonian site in Washington, D.C. All right, so here's our rule for at least 1. So the probability for at least 1 is 1 minus the probability of none. Or we can write it, the probability that x is greater than or equal to 1 is 1 minus the probability that x is 0, depending on what x stands for. So here's another example. So the new rapid COVID test gives quick results and is very accurate. The probability that the test will produce a false positive is 0.02. If the clinic performs 200 tests in a day on people who do not have COVID, so we know for a fact that they don't have COVID, what is the probability that at least one false positive will occur? So if you're not sure, a false positive means the test wrongly says that they do have the disease. All right, so we want the probability of at least 1. So we're going to write this out. Probability that at least 1 false positive is equal to 1 minus the probability of no false positives. All right, so let's see. It's going to be 1 minus the probability of, let's see, not false positive. And then we're going to do that 200 times. And we want to do this 200 times. So 200 times in a row, we're going to get not a false positive. All right, well, that's 1 minus. The probability of not getting a false positive is 1 minus 0.02. All right, so the probability of getting a false positive is 0.02. So the probability of not getting a false positive is 1 minus 0.02, or 0.98. Forgot the 200 there. So this is 1 minus 0.98 to the 200th. All right, so now when you raise a decimal to a number, this decimal gets smaller. So what ends up happening here is that gets smaller and smaller. In fact, that gets to the point where it's 0.0176. And if we subtract that from 1, we get 0.9824. So what's the probability of at least one false positive? Well, it's actually pretty high. 98% chance of that happening, or a probability of 0.9824. Pretty high. All right, so that means most of the time if it does come back saying positive, they give them a second test just to check, or they check for what other conditions they might have. All right, OUSD requires employees to submit to drug tests prior to being hired. The probability that these tests produce false positives is 0.005. All right, so the probability of false positive is 0.005. There are 400 teachers in the district, so we're doing this 400 times, who are all drug-free. What is the probability that at least one false positive? All right, so what's the probability that at least one of these tests is going to be wrong? All right, so, well, we got our at least one here, so the probability of at least one false positive is equal to 1 minus the probability of no false positives. All right, so that's equal to 1 minus the probability of someone not getting a false positive. 400 times. We're using 400 this time, right? All right, so the probability of false positive 0.005, so that means the probability that it's not a false positive is 1 minus 0.005, which is 0.995. So we get 1 minus 0.995 to the 400th power. So that gives us 1 minus 0.1346, which gives us 0.865. Oh, there it is right there. So the probability of at least one false positive, 86 to 87%, 86.5%. All right. So probably somebody's going to get a test that says that they are on drugs, even though they aren't on drugs. And this is why they always give them a second test if the test comes back positive. Right? Because that second test, probability of them getting 2 false positives is even smaller. Yep, there it is. All right, so that's how we deal with at least problems, and that's how the multiplication rules works with independence. We just multiply the probabilities together. This is the end of 5.3, so check out the homework for 5.3.